Welcome to Atomic Universe. I'm Dan Bergstrom, materials scientist. Today, we are going to take our first step into the subatomic world by examining the electron. Electrons are by far the most important of the subatomic particles. The modern world literally runs on electrons, like the ones that are bringing this video to life for you right now. From a materials point of view, understanding electrons will tell you everything you want to know about how atoms tick. Well, okay, not radioactivity, but pretty much everything else we're going to talk about in this video series. The plan for today is to review the history of electricity, discuss how understanding the nature of the electron has improved our understanding of atomic structure, and we'll end by showing a picture of what electrons moving around in an atom actually look like. Starting at the beginning, for the ancient Greeks, static electricity was a well-known but misunderstood phenomenon. Around the 6th century BC, Thales of Miletus was the first to write that rubbing pieces of amber on cloth or fur made them able to attract small particles. He also observed that lodestones, which are natural magnets, had similar powers of attraction. He concluded that these were both the same kind of attraction, which he believed must be due to a living force in the rocks put there by the gods. It was not until 1600 that static electricity and magnetism were documented as separate effects by Englishman William Gilbert in his treatise on the magnet and magnetic bodies. He noted that magnetic lodestones could only attract metallic objects, but that charged amber could attract both metal and nonmetals alike. He named the force in the amber after the Greek word for amber, which is electron. Writing in Latin, he coined the term electricus, but later writers translated this into English as electricity. Frenchman Charles François de Cisternet-Dufay noted in his studies on electricity, published in 1733, that there were actually two types of electric charge, which he called vitreous and resinous, and he found that opposite charges attracted each other while similarly charged objects repelled. Benjamin Franklin, often considered the first American scientist, became fascinated by electric phenomenon and made a dedicated study of it following his retirement from the printing business in 1748. He built his own static charge generator and discovered a way to increase the amount of charge that could be stored by hooking capacitive jars together in an array he called a battery. This was not a battery in the sense we think of it today, but more like a supersized capacitor whose voltage decayed as charge flowed out of it. Nonetheless, it allowed Franklin to study powerful static discharges and how to control them. Franklin found that metal rods with sharpened points were able to discharge static buildup more efficiently than other electrodes, and then he famously flew his kite into a storm to prove that lightning was the same kind of electricity he was studying in the lab. Ever looking for practical inventions, Franklin rolled these ideas together to create the lightning rod, a device able to protect tall buildings from lightning strikes by bleeding off static charges. Franklin wrote of these achievements in his 1751 work, Experiments and Observations on Electricity, coining many of the words we use today in the process. He spoke of electricity flowing as currents through conductors, from places of positive charge to negative charge. The battery as we think of it today was invented in 1800 by Italian Alessandro Volta. He was a professor at the University of Pavia, and he stacked copper and zinc discs together, separated by salt water-soaked cloth, in what became known as a voltaic pile, and he found it could supply a steady electric current at constant voltage. Immediately after word of how to make a voltaic cell reached England later that year, William Nicholson and Anthony Carlisle built their own out of copper coins and zinc plates, and immediately started experimenting with it. They found that when they put their energized electrodes into water, hydrogen bubbles formed at one electrode and oxygen bubbles at the other, discovering the process we now call electrolysis. Meanwhile, back at the University of Pavia, Volta's colleague Luigi Brugnatelli found that by applying a voltage to a metallic salt solution, he could induce metal to deposit out of the solution onto one of the electrodes, a process we know today as electroplating. As Italy was part of the French Empire at the time, Brugnatelli proudly showed off his invention to Napoleon by turning silver medallions into gold-plated ones. Napoleon's response was to declare electroplating to be a state secret, and so this work went unpublished for a number of years. But by the 1830s, the secret was out and attracted the attention of Michael Faraday, who ran his own experiments. Although it was to be another 50 years until current could be properly measured with an ammeter, Faraday cleverly put reaction cells in series so a matched current could drive multiple reactions. By doing so, he learned that the mass of different products from electrically driven reactions increased linearly as the applied current, and the masses of different products from the same current were in proportion to their atomic weight ratios. These became known as Faraday's laws of electrolysis after he published these findings in his 1839 book, Experimental Researches in Electricity. In this book, he coined additional terms we still use today, like ion, electrolyte, cathode, anode, and the associated terms cation and anion. For example, we can describe the principal reaction involved in copper electroplating as follows. Copper atoms from the anode enter the plating bath as positively charged anions after negative charge flows out through the anode. These anions then diffuse to the negatively charged cathode, where their charge is reduced back to zero by current flowing through the cathode. Faraday's work made clear that there was an intimate relationship between chemical bonds and the mysterious electric fluid. But it would be another 35 years before Irishman George Stoney would say that there must be something like an atomic unit of electric charge and use Faraday's laws to estimate it. But let's not get ahead of ourselves, because we're not done talking about Faraday quite yet. By 1838, Faraday had turned his attention to apply high voltage to gases, using gas tubes fitted with electrodes and rarefied air, essentially an early vacuum tube. He saw that high voltages induced electrical arcs in the tubes that started from the cathode and reached across to the anode. In 1857, German physicist and glassblower Heinrich Geissler used an improved vacuum pump to lower the tube pressure and found that instead of arcing, he could create a glowing gas that filled the tube. This is the same type of tube that was later developed into neon lights. We now know this glow is due to recombination of the electrons and ionized gases which coexist in electrical discharge plasmas. In 1860, German chemists Robert Bunsen and Gustav Kirchhoff published their study of the spectrum of light wavelengths emitted from both Geissler tubes and chemical flames made possible by Robert's new invention, the Bunsen burner. They found that light was emitted most intensely at a specific set of wavelengths that were unique to each atomic element, but the reason why remained a mystery for the next 50 years. In the late 1860s into the 70s, William Crookes in England and Johann Hittorf in Germany independently were working with improved vacuum pumps and developed what came to be known as Crookes tubes or Crookes-Hittorf tubes. And in these lower pressure tubes, glow discharge plasmas could not form, but there was still some radiation emitted from the cathode that could light up fluorescent screens. It was found that this radiation carried current to the anode, traveled in straight lines, and could heat objects in their path. German physicist Eugen Goldstein named these cathode rays in 1876. By the 1880s, atomic theory was on increasingly firm footing, with Mendeley's periodic table having correctly predicted the properties of several atomic elements prior to their discovery, and scientific consensus began to form that electricity too must come in discrete pieces. But as our friend George Stoney pointed out in an 1894 letter, he had been the first to show that there were atoms of charge some 20 years prior. Stoney had estimated this charge by applying Faraday's law to the electrolysis of water, along with an estimate of the atomic density of hydrogen gas he made using kinetic theory. His estimate was off by a factor of 16, but the name he later chose for the elemental piece of negative charge stuck, the electron. The stage was now set for J.J. Thomson to test the theory of the electron through his study of cathode rays. Thomson was able to determine the ratio of mass to charge for electrons by measuring the electric and magnetic deflection angles of cathode rays in a special Crookes tube fitted with electrostatic deflection plates. Published in 1897, Thomson's electron was astonishingly light, with a mass-charge ratio on the order of 1,000 times lower than a hydrogen ion whose mass-charge ratio could be inferred from Faraday's laws. These measured electron properties were the same for all combinations of cathode material and gas used in the Crookes tubes. So Thomson concluded that electrons must be identical components of all different types of atoms. Thomson is therefore credited as the discoverer of the electron, the first known subatomic particle, for which he received the Nobel Prize in Physics in 1906. The discovery of the electron was the first step in refining scientists' model of what atoms looked like. Building on the solid spherical atoms imagined by John Dalton, Thomson pictured the atom to be like a plum pudding, with lightweight electrons distributed inside a positively charged spherical atomic mass. But it would soon become clear this was not correct. The next hint as to what lay inside the atom began in 1896 with French physicist Henri Becquerel's accidental discovery of radiation, when he found uranium salt crystals stored on top of photographic plates created images in the film. In 1898, Marie Curie and her husband published her work on refining a radioactive ore called pitchblende into two previously unknown highly radioactive elements, polonium and radium. Becquerel and the Curies jointly received the 1903 Nobel Prize in Physics for their discoveries. Ernest Rutherford, a New Zealander working in England, studied this radiation further and determined in 1899 that uranium actually emitted two different types of radiation. What he called alpha radiation was only able to penetrate thin foils of metal, but his beta radiation could penetrate much thicker layers. The next year, Becquerel found that this beta radiation could be deflected by electric and magnetic fields just as Thomson had shown with electrons, and even the mass-charge ratio he measured was a match. Therefore, Becquerel concluded beta particles and electrons were one and the same. In 1906, Rutherford made similar measurements of the mass-charge ratio for alpha particles and concluded that they were doubly ionized helium atoms. He proved this in 1909 when he managed to capture enough alpha particles in a glass tube to make a glow discharge. When he analyzed the spectral lines, they were a match to the fingerprint of helium gas. Rutherford's best-known experiment with alpha particles came in 1911 when Heinz Geiger and Ernest Marsden, working under Rutherford's direction, focused the alpha particle source on thin gold foils to study how the particles scattered off the atoms within. Surprisingly, they found while most particles passed straight through the foil, the particles that didn't were scattered in all directions, including directly back at the alpha source. As Rutherford later described his shock at the result, it's almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back to hit you. Rutherford concluded that the mass of those atoms couldn't be distributed throughout the foil as dense packed solid spheres, but must be concentrated in small positively charged central nuclei. But that begged the question, where were the electrons? Rutherford knew of a solar system model of the atom proposed in 1897 by Irish mathematician and physicist Joseph Larmor, but there was a big problem with any atomic model with orbiting electrons. The circular movement of an electron would radiate electromagnetic energy in such a way that the electron would lose energy and its orbit would decay, spiraling into the nucleus. The key to understanding why this decay didn't occur came from the quantum theory of heat radiation. In 1900, an English baron and physicist Lord Rayleigh had calculated that the thermal radiation intensity emitted from hot objects at each frequency of light should be proportional to that frequency squared. While this formula worked well for the low-frequency infrared part of the spectrum, it predicted a very rapid increase in energy for higher frequencies that was not observed, in what was called the ultraviolet catastrophe. Later that same year, German physicist Max Planck proposed a solution to this problem, which was to assume that the vibrational heat energy in an object couldn't take on just any value, but had to be a quantized value, which meant it had to be an integral multiple of some minimum possible energy. He further assumed that this minimum energy was a linear function of the vibration frequency. Fitting his formula to the experimental data on blackbody radiation, Planck found the ratio of this minimum energy to the frequency to be 6.55 times 10 to the minus 34 joules per hertz, within 1% of the actual value of what we now call Planck's constant. Danish physicist Niels Bohr had started working in Rutherford's lab around the time of the gold foil experiments and took on the task of trying to find a better description of the atom than the solar system model. Inspired by the success of Planck's quantized energies, Bohr developed a model which quantized the electron's angular momentum as it orbited the nucleus. Bohr's model of the atom, which he published in 1913, had several key points. Firstly, the quantization of the electron angular momentum meant its lowest possible value was given by his formula with n set equal to 1, and the electron's orbit could no longer decay below that and spiral into the nucleus. Secondly, the energy as calculated from the quantized angular momentum was also quantized, meaning the electrons could only exist around the atom at precise energy levels. We now call these electron energy shells. Bohr extended this concept in 1922 to explain that each row of the periodic table corresponded to energy shells being increasingly occupied by electrons, moving from one electron in the first column to totally full shells for the chemically inert noble gases in the last column. Finally, this model was able to explain the strong spectral lines emitted by plasmas and flames as being due to photons that carry away energy released as an electron moved from a higher energy level to a lower one. Because of the quantization of energy levels, only wavelengths corresponding to the difference between two of these energies appeared in the atomic spectra. Notably, Bohr's model could predict the spectral wavelengths emitted by hydrogen gas very precisely without using any fitting parameters. Bohr won the Nobel in Physics for this work in 1922. Despite the successes of Bohr's atomic model, it was not clear why the energy electron should be quantized in this way, until, in 1924, when French physicist Louis de Broglie proposed the electron was both a particle and a wave as part of his PhD thesis. He calculated the wavelength of the electron to be Planck's constant divided by the momentum, and he showed that the allowed energy levels of the atom corresponded to the electron's wavelength wrapping around the atom n number of times. De Broglie won the Physics Nobel in 1929. This quantized electron wave model kept the electron in a simple circular orbit, which is not correct. but it was on the right track. In 1926, Austrian physicist Erwin Schrödinger took a three-dimensional conservation of energy equation written in terms of momentum and atomic potential, and applied de Broglie's equation converting momentum to a wavelength. The result was the famous Schrödinger equation, which, when solved, generates the three-dimensional electron orbitals we know today. One final improvement of Schrödinger's solution was obtained by Englishman Paul Dirac in 1928, when he solved it for the four-dimensional space-time version of the wave function to better account for the relativistic speeds of the electron motion. The fascinating world of Dirac's equation is beyond the scope of this video series, but I'll leave links in the description if you're interested to learn more. Erwin Schrödinger and Paul Dirac jointly won the Nobel Prize in Physics in 1933 for their contributions to understanding electrons and atomic theory. And that wraps up our discussion of the history of the electron. As we'll see in future videos, the chemical, electrical, thermal, mechanical, and optical properties of materials are all determined by interactions of atomic electrons. You could almost say the rest of the atom is just dead weight, but we'll explore that more next time. Before we end today, I would like to show you what is perhaps our best picture of what an electron actually looks like. This picture comes from the University of Lund in Sweden, where they have imaged electrons with attosecond laser pulses that are less than 10 to the minus 15 seconds long. With such a concentrated pulse of light as a flashbulb, it's possible to catch an electron moving in a freeze-frame snapshot like this one. Each pulse has a chance to kick an electron free of its atom, so a lower frequency laser is added to catch those electrons and nudge them back to their orbitals. The resulting image is actually a map of what is called the momentum space of an electron. Because the laser light will scatter differently off of electrons moving in different directions, the position of the scattered light in the detector used to make these maps will tell us how the electron was moving at the time the snapshot was taken. This map includes data collected simultaneously from many different atoms of argon gas and averaged together to reduce the signal noise. As you can tell from the rings of bright and dark intensity, there are allowed and forbidden values of electron momentum, just as Bohr predicted. By changing the relative timing of the two lasers, the electron can be imaged at different times in its motion. Here, with the lasers more out of phase, the shift in intensity towards the negative momentum values comes about because electrons kicked out of their orbit are being caught in the act of falling back into the atom. Finally, by assembling pictures from different laser offsets into a movie, electrons can be seen ringing through their energy levels as they re-enter their atomic orbits. And yes, the use of attosecond lasers to image electrons like this was recognized with the 2023 Nobel Prize in Physics. I hope you've enjoyed today's look at the electron. Thanks for watching.